Hi everyone, I am Kali Krishna. I will be presenting to you our work on sum rate maximization in NOMA-based mmWave analog beamforming under Imperfect CSI. The agenda of the presentation is the following. I will start with a brief introduction of technologies such as mmWave communication and NOMA. Later, I'd like to build on to the choice of architecture. I will then talk about the problem statement and then discuss the system model and problem formulation. Next, I will talk about the algorithm used to solve the optimization problem. Finally, I will talk about the simulation results in order to show the performance of the system. What is millimeter wave communication? Due to a tremendous increase in the capacity demands, there is a severe shortage of spectrum. So, researchers came up with the idea of using frequencies in the gigahertz range. Communication via these frequencies is millimeter wave communication. There are many advantages of millimeter wave communication such as large bandwidth, high data rates, low latencies, compact antenna packaging due to small antenna size, and very large beamforming gains. Despite these advantages, there is a major challenge that needs attention. This is the path loss. At such high frequencies, there is a large path loss. This large path loss leads to small coverages. So, how do we solve this problem? One solution is to use large antenna arrays. These large antenna arrays give rise to large beamforming gains, thereby improving coverage and reliability. Now, to utilize these large antenna arrays, what should the choice of architecture be? There are three types of architectures. First is a fully digital architecture. In a fully digital architecture, each antenna element of the array is connected to a dedicated RF chain. But at high frequencies, such as the millimeter wave frequencies, the antenna size is very small and a large number of antennas can be packed in small areas, and having so many RF chains will increase the cost and power consumption. To compensate this problem, another type of architecture is the hybrid architecture, where a low-dimensional digital beamformer is used in combination with an analog combiner. The performance of this architecture is very close to the fully digital one, but this has the disadvantage of having heavy feedback overhead between the digital and analog structures. So, in our paper, we employ the third type of architecture, where there is a single RF chain connected to the antenna elements. This has the lowest hardware complexity. There are two disadvantages of using a fully analog architecture. One, the conventional use of a single phase shifter makes the beamformer constraint non-convex. This problem can be overcome by using double phase shifters at each antenna element. This not only makes the beamformer constraint convex, but also gives rise to increase in degrees of freedom in terms of beamforming gain. Another disadvantage of using a fully analog architecture is information can be transmitted to a single user in a single resource block. This results in an inefficient usage of spectrum. So, to overcome this problem, we use non-orthogonal multiple access techniques as the radio access technique. Non-orthogonal multiple access technique, also called as NOMA, is a radio access technique where information can be transmitted to multiple users in the same resource block of time, frequency, or space. There are two types of NOMA, power domain NOMA and code domain NOMA. We prefer power domain NOMA because of its low cost implementation. In power domain NOMA, the transmitter superimposes information of all the users via superposition coding and transmits this superposition coded symbol. At the receiver end, information is decoded using a successive interference cancellation receiver. For successive interference cancellation to be successful, there are two conditions that need to be satisfied. These are the channel ordering condition and the power ordering condition. In this slide, I would like to talk about a very important aspect of system design, that is the channel state information. assumption that this channel state information is perfect is an unrealistic assumption, as in real time the obtained channel information is erroneous. Accommodating this into the system model will make the system robust to such errors. Particularly in NOMA scenario, channel state information plays a very important role as successive interference cancellation is dependent on it. Now, with this background, I'd like to talk about the problem statement. Our goal is to design robust beamformer and power allocation of a system with low hardware complexity. The obtained solution will be robust to channel estimation errors. This slide shows the system model that we proposed in our paper. There are NBS antenna elements connected to a single RF chain via a double phase shifter network. At the receiver end, there are K users with single antennas each. I would like to now briefly talk about the millimeter wave channel model that we employed in our paper. We consider the most popular channel model that models the millimeter wave environment, that is, the Saleh-Valenzuela channel model. The narrowband cluster representation is this. Next, I will talk about how channel estimation errors can be incorporated into the channel model. To make the system robust, channel estimation errors should be incorporated into the channel model. We consider an angle-based error model where we assume that the angle of departure estimated is not perfect. We can see that here in this equation. By using Taylor series approximation, we reduce the angle-based error model into a simplified additive error model as this. Now, with this background, I'd like to talk about the problem formulation. The problem is formulated as a sum rate maximization problem. The constraints convey information as follows. The first ensures that the power allocation does not exceed the total available power and that it also follows the power ordering condition of NOMA. The second constraint is the channel ordering condition of NOMA. The last constraint is the double phase shifter based constraint on the beamformer. But this method of formulation is non-convex in nature, so we reformulate it as a weighted MSE minimization problem that we see in the next slide. Here, in this slide, we see the sum rate maximization problem being reformulated as a weighted MSE minimization equivalent. The constraints convey information as before. The proof showing equivalence between sum rate maximization and weighted MSE minimization is given in detail in the paper. Now, to solve this problem, we propose an iterative algorithm that will be seen in the next slide. This is the iterative algorithm that solves the weighted MSE minimization problem. Finally, I would like to talk about the simulation results that we presented in the paper to evaluate the performance of the proposed system. The first plot shows the performance of the proposed robust design in comparison to a non-robust system at different error variances. We see that by incorporating an appropriate channel estimation error model, the performance of the system improves. The next plot shows the performance in comparison to a system under perfect CSI assumption. This is shown as a bound. Next, to the left, we see the performance of the robust system as the number of antennas increase. We see that the performance of the system increases as the number of antennas increase. Finally, to the right, we present the convergence plot that shows the proposed algorithm converges in few iterations. To summarize, we proposed a system with low hardware complexity that is robust to channel estimation errors. To design this system, we formulate the problem as a sum rate maximization problem. But because of the non-convex nature of the formulation, we reformulate it as a weighted MSE minimization problem. We then discussed an iterative algorithm that solves the problem and results in an optimal beamformer and power allocation. Finally, we evaluate the performance of the system via simulation results. These are some of the references. Please do reach out to me if you have any other questions. Thank you.